So when we talk about specific heat capacity, we are talking about the amount of thermal energy, sometimes referred to as heat, needed to raise the temperature of 1 gram of a substance by 1 degree Celsius. The amount of thermal energy needed to raise the temperature of 1 gram of a substance by 1 degree Celsius. The symbol we use for specific heat in equations is a lowercase c. And we will typically report the units for this value as joules per grams times degree Celsius. So I know that looks kind of intimidating, but it's literally the thermal energy, joules, that's what we measure energy in, required to raise the temperature of 1 gram of a substance by 1 degree Celsius. So the units are in the definition, essentially. Another way to write this is you could do the grams in the degrees Celsius to -1, but you'll typically see it written as like joule / grams times degrees Celsius. That is the unit. The specific heat, the value associated with the specific heat of a substance is dependent also on the state or the phase of the substance, aka whether it is a solid, a liquid, or a gas. Different states will have different specific heats. A great example of that is water. You look at water. Water, we talk about 3 states in this class, solid, liquid, and gas. Water can exist as liquid water, it can exist as ice, solid water, or it can exist as water vapor, water in the gaseous form, okay? You will notice that liquid, solid, and gaseous water each have different specific heat values associated with them. Specific heat is dependent on the state. Also, as a note, you do not need to memorize this table. The specific heat for liquid water, solid water, and water vapor are all listed on your formula chart. Just an FYI. The specific heat of ice, water, and steam are all listed on your formula chart. If you needed the specific heat of any of these other things for a problem, we would either give it to you or we would give you all the other information you needed to solve for it yourself. So this is not something you need to memorize. Just an FYI. And just another little for your information piece of information is that specific heat is known as an intensive physical property. So you can actually identify a substance by its specific heat. We don't talk a whole lot about intensive versus extensive physical properties in this class anymore since it's not in the TEKS. But we can use the specific heat, solve for the specific heat of a substance, and use it to identify that substance, which is actually what we are going to do in our calorimetry lab later this unit. We'll be able to identify specific metals by calculating their specific heat, and then look at a table like this to figure out what our metal actually is. But that is kind of our intro to specific heat, the background information on it. We're going to talk a little bit more about how this information can be applied to specific substances. One thing about specific heat is that dependent on whether or not specific heat is high or specific heat is low will affect the kind of temperature change you'll see when you expose a substance to a certain amount of energy or allow it to absorb or give off a certain amount of energy. So if you look at a substance with a low specific heat, for example, so some things with low specific heats, a lot of our metals, copper, lead, iron, these things have fairly low specific heat when we compare them to things like water. These things are known as good conductors. So they're great at conducting heat because what you're going to see is there are large temperature changes associated with small energy changes. That means it does not take, you don't have to put in a lot of energy to get these substances with low specific heat to increase in temperature. You can put not very much energy into lead. You can get lead to absorb not a whole lot of energy, but even if it's not absorbing a whole lot of energy, you'll still see a greater temperature change than you would see, say, if you had that same amount of energy being taken up by water. So on the other end of that, you have something like water, which has a high specific heat. Things with high specific heat, air also has a fairly high specific heat when you compare it to substances like metals. These things are good insulators, and you've probably or hopefully heard before that air is a good insulator. That's why when it gets really, really cold out, like it is out today, it's really nice to wear a big puffy jacket that has a lot of air in between you and the outside of the jacket, because that will insulate you a lot better against the cold. See some light bulbs going off in your heads right now. Yes, that is why puffy jackets are great for very, very cold weather days. So good insulators, that means they have typically small temperature changes associated with even large energy changes. So something like water, you think about water, this also goes back to why areas along the coast, places like San Diego, are a lot more regulated by the being close to the ocean in terms of temperature. There's a lot less variation in their temperature and their climate year-round. There by the water, water is great at regulating climates because water can absorb a large amount of energy without changing very much in temperature. That just goes to the fact that water has that high specific heat. You may have talked about this in first-year bio last year, because water is a big topic of interest for biologists. So that is kind of the difference between high and low specific heat. The example we have down here aims to kind of clarify why it's so much nicer to be in the water on a hot day at the beach than it is to be barefoot on the sand on a hot day at the beach. If you think about a sunny day at the beach, the sand is quite hot and the water is nice and cool, and so you tend to want to run to get to the water real quick when you take off your shoes. That has to do actually back with specific heat as well. So the specific heat of sand, if we were to measure the specific heat of sand, it is 0.78 joules per grams degrees Celsius, whereas the specific heat of liquid water is this 4.184 joules per grams degrees Celsius. Okay? So what do we notice right off the bat about the specific heat of water compared to the specific heat of sand? Yeah. Water is much higher than the sand, right? A lot higher specific heat in the water there than the sand, okay? So sand, we can see, has that smaller specific heat value. So what you're actually going to notice there, why is the sand so hot but the water is so cool? Okay? You see that greater change in the temperature of the sand than in the temperature of the water. When they both absorb the same amount of thermal energy or heat. And I do like to clarify, it's thermal energy. Okay? So greater change in the temperature of the sand than in the temperature of the water when they both absorb the same thermal energy amount. Okay, so it's a hot day at the beach. The sand and the water have both been sitting out in the sun just as long as each other. But the water has a much higher specific heat, so it can absorb a lot more thermal energy without changing temperature than the sand can. So this is why you want to run to the water to get off that hot, hot sand. What questions do y'all have about this? Okay. If we don't have any questions about this so far, we're going to go ahead and flip to page 9. And we're going to start getting into calorimetry. Okay? So, calorimetry. Say that with me, y'all. Calorimetry. Say it again. Calorimetry. Calorimetry. Okay, calorimetry. Got it. Okay, so calorimetry, this is a technique that is used to determine the heat change in a reaction or a process. Since we cannot measure heat directly in the laboratory, we are going to measure the magnitude of the temperature change. The magnitude of the temperature change caused by heat flow. So, this is remember that heat is the movement of thermal energy. So we can measure the temperature change that results from the movement of thermal energy. And a calorimeter is a device that is used to measure this heat flow. So when we start getting into calculations, we are going to use something called the MCAT formula. It's called the MCAT formula because it looks a little bit like, MCAT, MC delta T. The delta looks a little bit like an A, so we'll often call it the MCAT formula. What this formula is this is a formula for the heat change or the enthalpy change here in joules, which is also sometimes Q. So delta H or Q can be used interchangeably. We say that delta H or Q is equal to MC delta T. M being mass, C being the specific heat, and delta T being the temperature change. What I want you to keep in mind as we look at this formula, with this formula, anytime you plug in values to this formula, you must make sure that your units match. Okay? There's a lot of different values that we're going to plug into this formula. And so if you look at something like enthalpy measured in joules, you want to make sure, that these things match. Your specific heat is typically going to come in joules per grams times degrees Celsius. So what you get spit out at the end if you're solving for enthalpy is going to be in joules. If you are given a value in kilograms, your mass in kilograms, you're going to want to make sure you convert that to grams because, again, remember, specific heat here is going to be measured in this joules per grams degrees Celsius. So we want to make sure our mass is also in grams over here. Temperature, it's not as big of a deal because this is a magnitude of temperature change. If you change 15 degrees Kelvin, you're going to change 15 degrees Celsius as well. So this one can technically be in Kelvin or Celsius, but you will notice, of course, that your specific heat is given to you over here in per degree Celsius. So just something I wanted to point out. We want to make sure that our units match whenever we use this formula. Something to keep in mind. This will, if we're using specific heat in joules per grams times degrees Celsius, we're going to get our enthalpy spit out to us in joules. And so if it's asking you for something in kilojoules, you might have to convert there as well. Just things to keep in mind. So that is our formula for calorimetry, and I want to show you what a simple calorimeter looks like, or talk a little bit about simple calorimetry. The basic idea here of this structure, this setup here, this calorimeter, is to measure what is happening with the surroundings to make some assumptions about what's happening with our system. And so our system can be a couple of different things. It can be a reaction. It can be like a piece of metal or something. In this specific case, we have our system. We're going to say our system is our reaction, and the surroundings is everything else. So here's of course, our reaction mixture in our solution. So a lot of times in a calorimeter, you'll have, your reaction. It might be taking place in water, as we have it is the case here. With this reaction, taking place here. Everything else around it is considered the surroundings, okay? So the surroundings here, our water would be our surroundings, our cups that we're using to insulate this system here. These are some styrofoam cups to insulate our surroundings. The stopper, the thermometer, these things are all the surroundings, okay? And I want to draw your attention to the fact that we do have a thermometer in this setup. I said that, we are going to use a calorimeter to measure what is happening with the surroundings, to make assumptions about what's happening with the system. In order to measure what's happening with the surroundings, we're going to be measuring the temperature change of our surroundings, okay? So this thermometer here is going to be helping us to measure the delta T, the temperature change, that we can use to solve some of these MCAT equations that we're going to be looking at shortly. So a thermometer will always be some part of our calorimeter setup here. So as we are looking at this calorimeter, if we have a reaction going on in our calorimeter, we can make some observations. We can, of course, record temperatures, starting and ending temperatures with the thermometer. If the temperature of the water, the surroundings, go up, the temperature of the water, the surroundings goes up, that's going to feel warm to us. Okay, we feel that as temperature's going up, we're like, okay, that's getting warm. As the temperature of the water goes up, then the process or the reaction, aka the system, must have released energy. The temperature is going up because the reaction released energy to the water. The water is absorbing that energy, is going up in temperature. Okay, so if the reaction or the system released energy, what type of process is that going to be? Endo or exo, y'all? Exo, very good, y'all. Remembering from last class that exothermic reactions release energy. Great recall. The opposite scenario can also take place. We can have a case where the temperature of the water or the surroundings goes down. So what would that feel like to us, y'all? Cold. It's going to feel cold. The temperature goes down. It's going to feel cold, just like it feels cold outside right now. That means, if it's going to feel cold, that means the process must have absorbed energy. Okay, the water's feeling cold because some of the energy was taken out of the water. The process must have absorbed energy. What do we call those reactions that absorb energy from the surroundings? Endothermic. Very good. Process is endothermic. Taking it in. Taking in that energy, absorbing that energy. And we can measure, essentially, we can second-handedly measure that absorption or that release of energy by measuring the temperature change that's going on with the surroundings, the water here. Is anyone still using what I have up on the board? Okay. So this last little bit we're going to write in and fill in before we start doing some calculations has to do with some assumptions we're going to make with our calorimeter. Okay, so that calorimeter on our page over here, so the one that you see here, this is actually, it's using some styrofoam cups. This is what I like to call a discount calorimeter. We're using some styrofoam cups and some little stoppers and so on and so forth. And it's not a lab grade one. The one we're going to use in class during our lab is also going to include some styrofoam cups. It's not going to be a perfectly insulated system. But when we do our problems in chemistry, especially in first year chem, what we are going to assume with our calorimeter is that this container is perfectly insulated, even though it's technically not. We're going to make an assumption when we do our math for these problems that the container is perfectly insulated. And so if we imagine the container to be perfectly insulated, that means that there's essentially equal transfer of thermal energy from the reaction to the surroundings, vice versa. What we can say then is that the heat change of the process is equal to the opposite heat change of the surroundings, aka the water in this case. The heat change of the process, or reaction, as it sometimes is. Sometimes it's just a process. Sometimes it's a reaction. The heat change of the process or the reaction is equal to the opposite heat change of the surroundings, the water. To put that in math terms, so it makes a little bit more sense for our brains, hopefully, we can use these expressions here, okay? So this says that the heat change of the system is equal to the opposite heat change of the surroundings, or vice versa, right? So what this is telling me here is that the amount of heat absorbed by the system is equal to the amount of heat lost by the surroundings, or the amount of heat released from the system or the reaction is equal to the amount of heat absorbed by the surroundings. So we are going to assume at this level that all of the heat given off by the process will be absorbed by the water, or vice versa, and that no heat was given off to anything else in the setup. This is what we mean by a perfectly insulated interaction. All of the heat given off by the process will be absorbed by the water, or vice versa. The vice versa is that all of the heat absorbed by the process will be given off by the water, and no heat will be given off to anything else in the setup. That's what we mean by a perfectly insulated system. In reality, there is some heat absorption by the calorimeter itself, as well as some heat loss to the surroundings, as in this is not a perfectly insulated system, but we're going to pretend it is for the sake of our calculation. So just something to keep in mind as we start getting into the math of things down here. Any questions so far? Hopefully, if you are confused at this point, doing this problem will help us kind of contextualize and make sense of this. I think some people have an easier time of understanding things once we start getting into the math. So we're going to do this first problem. We're going to start off today by doing some calorimetry calculations involving metals. There are lots of different calorimetry setups. One of them involves metals, and this is one such example. So what's nice is this is broken up very nicely into the different parts that we are essentially going to analyze. And all of the information we need to solve this problem is included up here. All of the information needed to solve this problem is included up here in this paragraph, as well as a little bit of information down here. So what I like to do when I am given information for a calorimetry problem is I like to write out everything I know about the substances in the problem. So here we are told, first read through, that a piece of metal with a mass of 15 grams was sitting in a boiling water bath at 100 degrees Celsius. The metal was then removed from the boiling water and quickly added to a sample of water in a styrofoam coffee cup. Styrofoam coffee cup calorimeter. The water in the coffee cup had a mass of 100 grams and was at the initial temperature of 25 degrees Celsius. The specific heat of water, we are told, is 4.184 joules per grams times degrees Celsius. So I'm going to write out everything I know about the metal and the water in this example up here. So let's start with the metal. This metal, we are told, has a mass of 15 grams. So its mass is equal to 15 grams. We also know a little bit about the metal's temperature. We know the initial temperature of the metal. The reason we know that is because we are told the metal was sitting in a boiling water bath at 100 degrees Celsius. Okay? So we assume that the metal was sitting in this boiling water bath at 100 degrees Celsius for some time. and has at that point also gotten to 100 degrees Celsius. So if you're told that something's been sitting in its water bath, you're going to assume that is its initial temperature. It's been sitting in there for quite some time. It is also 100 degrees Celsius at this time. So the initial temperature of the metal is 100 degrees Celsius. We also know some information here about the water. Okay. We are told with the water here, we know that the water has a mass as well. The mass of the water is 100 grams. We also know the initial temperature of the water. We know the initial temperature of the water, and I'm going to abbreviate that again as T subscript I, initial temperature of the water, is 25 degrees Celsius. We were also given the specific heat. So I'm just going to write specific heat of the water is 4.184 joules per grams degrees Celsius. So that's everything we know about the water at this time. And knowing this information, we are also told, of course, that the metal was removed from the boiling water at 100 degrees Celsius and was quickly added to a sample of water in a styrofoam coffee cup calorimeter. So it was added, the 100-degree metal was added into the 25 degrees Celsius water. When the metal, the 100-degree metal, is dropped into the 25 degrees Celsius water, what is going to happen to the temperature of the metal, y'all? Is it going to go up or is it going to go down? Just do thumbs up for up, thumbs down for down. It will go down, yes. If you put 100-degree metal into 25 degrees Celsius water, the metal's temperature will go down, okay? So the metal is going to cool down, temperature is going to go down. What's going to happen to the temperature of the water once the metal, the 100-degree metal, is placed in there, y'all? It's going to go up. So it's going to warm up or heat up. Very good. That's just kind of observations in the world, right? If I drop something really hot into some cold water, think about metal. You're going to hear a little sizzle as it cools down a little bit. And the water heats up a little bit. We are told here in part C that at some point the metal-water mixture reaches thermal equilibrium. So it's going to reach thermal equilibrium at a temperature of 25.35 degrees Celsius. What thermal equilibrium means is that the temperature of the surroundings and the temperature of the system are equal, aka the temperature of the metal and the temperature of the water are going to be equal at 25.35 degrees Celsius. So now we have a last little bit of information for both the metal and the water here. We knew the temperature, the initial temperature, from this paragraph up here. I now know the final temperature of both the water and the metal. It is 25.35 degrees Celsius for both of them. This value will vary depending on the problem. It's not always going to be 25.35 degrees Celsius. But for this problem, for this specific piece of metal, at this mass and in this amount of water, the thermal equilibrium temperature, the final temperature, T little subscript F, is 25.35 degrees Celsius. So we have quite a bit of information about the metal and the water. We can use that information that we have so nicely laid out to calculate now the change in temperature for both the metal as well as the change in temperature for the water. So this next step, step C, or letter C, is asking us to calculate delta T for the metal as well as delta T for the water. And delta T, just so y'all know, delta T is always going to be the final temperature minus the initial temperature. So you can plug those values in for the delta T of the metal, final temperature of the metal, 25.35 degrees Celsius minus the initial temperature of the metal, 100 degrees Celsius. Okay. What was the final temperature of the water, y'all? 25.35. What was the initial temperature of the water? 25. Okay. So you can do these calculations using the calculator you grabbed today. So 25.35 minus 100. If you don't want to do this in your head, I am in scientific notation mode. Put my back. I get, negative 74.65. If I wanted to, be really on top of my sig figs, this should technically be negative 74.7, but we're just going to go ahead and leave it like this. It's fine. And then, so that's our change in temperature here. What's our change in temperature going to be here, y'all? .35 degrees Celsius, yeah. Yes, sir. So for this one you can keep it negative. Yeah. Because the temperature change, if you keep your values negative or positive, that's going to help you hopefully figure out whether or not you're releasing or you're absorbing energy there at the end. That can help with those. Okay. Any questions so far, y'all? So now we reach letter D, which is a fill in the blank. It says, assuming that no energy was lost by the calorimeter, again, assuming perfect insulation, the amount of heat lost by the metal, okay, so the amount of heat lost by the metal is blank the amount of heat gained by the water. Let's say up here, y'all. Yes, basically equal to an opposite. So the amount of heat that is lost by the metal is equal to the amount of heat gained by the water. So whatever thermal energy has been lost by the metal should be then gained by the water. We are assuming a perfectly insulated system with perfect heat flow, complete transfer of energy. So using that, knowing that, we can calculate the heat change of the water as well as the heat change of the metal. So calculating the heat change of the water, using our equation of Q or delta H equals MC delta T, we can calculate specifically the heat change of the water. So with this equation, we're going to be careful to plug in values that we know from the water. So we did a great job up here of writing down all of our information, and you're going to do a great job every single time you go and tackle a problem like this, of writing down all the information you know about your water and your metal or whatever it is you're dealing with in that specific problem. That way you don't get confused, because when they ask for the heat change of the water, they want us to fill in the M, the C, and the delta T that go with the water. So with our water here, we're going to calculate the heat change, aka the Q or the delta H. We know the mass of our water. We wrote down that it's 100 grams. We know the specific heat of our water. We were told in our problem, 4.184. That's also on your formula chart, just an FYI. Okay. We also know the delta T. We actually already calculated the delta T, so we don't even need to do this 25.35 minus 25 here. We can just pop in the temperature change we already calculated. And then we can calculate, our answer in 4 sig figs, since all of our values for our water was given to us. Here we have these 3 values all had 4 sig figs. Let's do 100 times 4.184 times 0.35. We get this value. And if you did your temperature, your final minus initial temperature correctly here, then your heat change should have the correct signage associated with it. So this is in joules because our enthalpy is always going to be in joules if we're using a specific heat in joules. It's going to be positive, a positive value. So we said that the temperature of the water warmed up, it went up. Okay, so this is the amount of energy gained by the water here. So what's the heat change of the water? That is the heat change of the water that we just calculated. Knowing that the amount of heat lost by the metal is equal to the amount of heat gained by the water, would anyone like to try and tell me what the heat change of the metal is going to be? Yes, negative 146.4 joules is lost by the metal. That's the heat change of the metal. And we know that because we were able to observe the water and do this MCAT calculation with the water, the surroundings. What questions do we have so far? And then knowing the heat change of the metal, using the heat change of the metal, we can calculate the specific heat of the metal. Okay, we didn't know the specific heat, we weren't given that, but we can calculate it knowing what we know here. Okay, so Q or delta H, however you want to, phrase it here, that's equal to MC delta T. And in this case, we know the heat change, so we're going to plug that guy in over here. Remember, we're looking at the metal now. So we're looking at the metal now. So using our values that we have for the metal, what's our mass of the metal, y'all? 15. Very good. 15 what? Grams. I like to include my units here so I make sure everything is lining up as it should. My units all jive with each other. We're trying to calculate the specific heat. Remember, specific heat is C. So we don't know that. We're going to try and calculate that. And then we have delta T. What's our delta T for this? We actually already calculated it. Negative 74.65. Very good. So now we can just calculate that. So go ahead, try and see if you can calculate that. Just your basic algebra, and then I'll do it with y'all up on the board so you can check yourselves here in a sec. Okay, so hopefully you're able to type this out and just divide by the product of these two values here. Does anyone want to share what they got with me before I click this? .13, yeah. So you should get this value, hopefully if you typed everything in correctly to your calculator. I'm going to go ahead and just go to 4 sig figs here, 0.1307. And then what's our unit for specific heat, y'all? Celsius is part of it. There's actually 3 units in there. Joules divided by grams times degrees Celsius. There we go. Very good. I know, it's kind of weird. If y'all, if you're ever like, oh no, I don't know how to do my specific heat unit, come over here on your formula chart. If you look above the metric prefixes, there's some constants and conversions. Look at your constants, your water, ice, and steam specific heat. They have the unit listed right here. So if you're like psyching yourself out, you're like, I don't remember how to write it correctly, just come look here. It's listed correctly right there. Okay? So that is our specific heat there. What questions do we have about that problem? Cool. We're going to go ahead and flip to the next page. I want us to spend about the next 5 or 6 minutes, working on this problem. I want y'all to write everything you know about the metal from this little paragraph here. I want y'all to write everything you know about the water. And then I want you to try and calculate the heat change of the water, the heat change of the metal, and then the specific heat capacity of the metal. So try and do that. We will check our work here in a sec. Okay, let's go ahead and start going over what we have here. Would anyone like to tell me what they calculated for the heat change of the water? Anyone think they got it? Say it one more time. 1715. So 1715, you should get a positive value if you typed it or you did your final minus your initial temperature correctly. You should get a positive value. So you could put a plus there, or you could leave the plus off, and I would just assume that it was a positive number, as that's how positive numbers work. So joules. So is this energy that was gained by the water or lost by the water, y'all? Gained. Very good. Gained by the water. So if you wanted to, you could just do the 1715 joules. I'm just putting gained by the water to help y'all hopefully internalize the fact that since this is positive, it is being gained. So what is going to be the heat change of the metal then? Negative 1715. Very good. So there's that much energy, equal and opposite amount of energy, basically. This is the amount of energy that was lost by the metal. And we can use that, of course. What is this going to be in our MCAT equation down here, y'all? The delta H. Very good. So the negative 1715 joules. And then we just plug in our metal values, right? So what was the mass of the metal that y'all calculated? 59.05 grams. We're going to solve for specific heat. And then what was our final temperature, y'all? $27.80? Yeah. 27.80 minus our initial temperature, which is the other one. So you should get a C value of what? 4023. Very good. And then our values again. If you get tripped up and you're like, oh no, you can go back up here. You can look at the specific heat units for the water. You should be able to pop that in there. What questions do we have about that problem, y'all? Okay. If we don't have any questions at this time about that problem, we're going to go ahead and do this last combustion calorimetry problem, and then I'll give you the answer for the second one so you can check your work. So we just did calorimetry involving metals. That's how you would do any kind of metal calorimetry problem. The other type of calorimetry problem you may run into in this class is a combustion or burning calorimetry problem. So here are some examples of calorimetry setups, calorimeter setups that have to do with combustion. This is like a lab grade combustion calorimeter. This is what I like to call the discount calorimeter because it's basically made with stuff you can find at a dollar store. So here you have a very simple setup, I think, to think about if you're looking at our little discount calorimeter. You have a food piece or a substance that you're testing, that you're combusting, and then you have the water, of course, that can be heated by the energy released from combustion reaction. So your samples here, your food to be tested, your cup holding your sample, these are your samples to be combusted. Your samples to be combusted. If combustion reactions are releasing energy, what type of reaction would we say that these are, exo or endo? Releasing energy is exo or endo? Exo. Very good. Combustion is exothermic. So you've got your samples to be combusted, and you, of course, you still have a thermometer. Here, I know this isn't pictured, but there should be a thermometer here as well. Should also have a thermometer in our little discount calorimeter. Remember that the thermometer is to measure the delta T. We have to measure the final and the initial temperature in order to actually do our MCAT calculation. So that's what the thermometer is there for. And a very similar concept in that we're going to want to measure the final and the initial temperature of the water in order to make some assumptions about what's going on with the reaction or the process. In this case, it's a reaction, combustion reactions. And in this first example here, we are given the example of 0.303 grams of sucrose burning in a calorimeter. We are told the amount of water in that calorimeter, and we're also told about the temperature change here in this reaction. So essentially what we have setup wise is you have, a little container of water. There's our water. And we have a sample of sugar, some sample, in this case it's sucrose, that's being burned. And we know some information about this whole setup here. We are told we have 0.303 grams of sucrose, so the mass of the sucrose there. We're also told some information about the water. We're told that we have a mass of 240 grams of water. We're also told the initial and final temperature of the water, okay? So we're told that the water changed from 22.53 degrees Celsius to 27.55 degrees Celsius, okay? So what is the initial temperature of the water, y'all? 22.53. 22.53 degrees Celsius, leaving the other value our final temperature. It's going from the initial to the final. We also know that the specific heat of water is 4.184 joules per grams times degrees Celsius. Well, that's all the information we know. And we are tasked with finding the heat change of the sugar. I want you to notice here that I was not asking for the heat change of the water, but as a reminder, the heat change of the sugar is going to be equal and opposite to the heat change of the H2O. So heat change of the sugar is going to be equal and opposite to the heat change of the H2O. So if we were to calculate the heat change of the water, we could use that to help us figure out the heat change of the sugar. So let's go ahead and do an MCAT calculation using what we know about the water. So I'd like y'all to try and calculate the heat change of the water and then use that to figure out the heat change of the sugar. So go ahead and do that. We'll check our work here in a second. So double check that those are the things that you filled in for the values in your MCAT equation correctly. You should have gotten 5,040. If you want it to be in 3 sig figs, 5,040. If you got 5,041, that's 4 sig figs. That's fine too. Okay. If we're looking at, 3 sig figs here, this much, what's our unit going to be? Joules. Very good. Joules. So we've got this amount gained by the water. So what does that tell us about the delta H of the sugar, the sucrose, y'all? Negative 5,040 joules lost by the sugar. Yes, you may. So that is our heat change of the sugar. Using the heat change of the water to help us figure out the heat change of the sugar. What questions do we have there? Yes, sir. Oh, the number of sig figs for this? Oh, yeah, 50-40. So since the decimal is absent, we start from the Atlantic Ocean side, which is this side. We start counting at the first non-zero digit. So 1, 2, 3 sig figs. Yeah. With these calorimeter problems, the thing that is kind of funky about these guys is that there's also, it depends, when you're adding or subtracting, you're using different sig fig rules for adding and subtracting, and then once you have those amount of sig figs, and that factors into your calculation as well, and so they can get a little bit funky. So we're not, we're not going to be super stingy about our sig figs and how we award credit in that aspect. Basically, same rules as some of our previous units, where I would really like you to not give me a string of 18 digits if you have, a decimal with many, many numbers coming after that decimal point. So as long as you're within that range of sig figs that we're looking for, you should be fine. Yeah. Any other questions? Good question. I'm sure Ms. Marusik would also tell you if you want to go on to take AP Chem, that their not going to make a calorimetry problem, the sig fig question. There's usually like one sig fig question on the AP Chem exam, and it's usually like a reading instrumentation question. Sometimes it is it's associated with dimensional analysis, but I can't remember her ever telling me it being associated with the calorimetry problems. So we're not going to be stingy about that because this is a class meant to prepare you for that class. Okay, so last couple letters, B, C, and D. Hopefully we can knock these out with limited confusion. This one, I want you for sure, like, you definitely need to know how to do this, okay? This figuring out the heat of combustion in kilojoules per moles. This will show up again and again in both this class, on your progress checks, on your tests. It'll show up again in AP Chem. This is kind of a, hey, let's play food chemist here for a second and do some dimensional analysis, because what they're asking us to do in letter B, for example, is to convert our heat change of our sugar. They want us to convert our heat change of our sugar to food calories, which is what food chemists do. So the reason we actually know how many calories a food item is actually going to provide you with, for example, is due to this whole combustion calorimetry process and converting the heat changes that we calculate to these food calories. So here we're told, for example, that 1 food calorie, in other words, capital CAL, is equal to 1,000 heat calories, lowercase CAL, and 4.184 joules is equal to 1 heat calorie here. And so, let's convert this into food calories as referring, of course, to our negative 5,040 joules that we got in our previous problem. We could, if we wanted to, convert that into food calories, figure out how many food calories that amount of sugar is. Could be released from that amount of sugar, essentially. And so what you're going to do there is you're told, this many joules is equal to 1 heat calorie. So you could go from joules to heat calories, which is lowercase CAL. And then you could go from heat calories with this conversion to food calories, which is capital CAL. Okay, so we could do this 2-step dimensional analysis to convert. So I start with 5,040 joules using my little roadmap I built myself over here. We could do a quick little 2-step dimensional analysis based on the conversions we're given here. We're told that 4.184 joules is equal to 1 heat calorie. So we can go from joules to heat calories in this first step. We know there's 4.184 joules in 1 heat calorie. And then we can go from heat calorie to food calorie. So just really trying to differentiate my lowercase and my uppercase c, since they don't really look much different other than the size. I'm told, of course, here that 1,000 heat calories is equal to 1 food calorie. And so we can convert this value to food calories. You know, 5,040, or let's see, negative 5,040 divided by the product of these two numbers. So I'll just open up a parenthesis and do 4.184 times my 1,000 here. Thank you, ma'am. And I get this negative 1.20. Okay. And you might be thinking, okay, wait, like we don't put calories or food calories in negative values. Basically what this is saying is, with that 0.303 grams of sucrose, upon, processing that sugar, releasing that exothermic reaction happening, you could release, 1.20 joules or this many food calories worth of energy from that, and so typically we'll just say, it's a positive value, 1.20 food calories. We don't typically put negative values with food calories. But this is how much energy could be released from combustion of that amount of sugar. So some energy that could be available for use if a person were to, digest that or whatever. Okay? So that's just kind of that basic dimensional analysis there. The next step is the problem you'll see, you'll encounter much more frequently. You will often be asked to find the heat of combustion in kilojoules per moles. So if you're asked to find the heat of combustion in kilojoules per moles, you're going to have to do some conversions again, because right now you have an amount of energy in joules and you have an amount of sucrose in grams, but you want this in kilojoules per mole. So what you're going to have to do to figure out heat of combustion in kilojoules per mole is you're going to have to convert your number of joules to kilojoules. You're going to have to go from joules to kilojoules. And you're going to have to go from grams. So you had, 0.303 grams of sucrose, which is C12H22O11. So you will have to convert your joules to kilojoules and your grams of your substance to moles. Once you do that, you can take the kilojoules and divide it by moles to figure out your heat of combustion. So we know that there's 1,000 joules, or 1 times 10 to the 3. Just use your numbers here. There's 1 times 10 to the 3 joules in 1 kilojoule, 1,000 joules in 1 kilojoule. And then if you were to calculate the molar mass, if you do, 12 carbon, 12 times 12.01, you do 22 hydrogen, okay, plus 22 times 1.01, that's the molar mass of hydrogen. You look at your periodic table, plus your 11 oxygen times the 16, which is on your periodic table. You can get this as your molar mass, okay, 342.34. There's 342.34 grams of sucrose in 1 mole of sucrose. For the sake of time, I'm just going to calculate what I had calculated last period for my previous class. So this, you should get negative 5.04 kilojoules. And for this one, you should get 8.85 times 10 to the negative 4 moles. If you divide this number of kilojoules by this number of moles, remember kilojoules per moles, you will get negative 5.69 times 10 to the 3 kilojoules per mole, or negative 5.690 kilojoules per mole. Either one is fine. One is in scientific notation, and one is in standard notation. But there is your kilojoules per moles. And that's how you would solve that. Okay. So if we are releasing, this much energy from our reaction, from our combustion of our sugar, would you say that this combustion, or any combustion reaction for that matter, is endo or exothermic, y'all? Exothermic. Should heat therefore be listed as a reactant or a product in the combustion reaction? Product. Very good. Product. And just as a reminder, If you were to draw out the reaction progress potential energy diagram for this reaction, you would put the products at a lower level of potential energy than the reactant. And if you would like the answers to the problems below, to practice and check your work, I will go ahead and list them out here since I gave them to last class as well. So there's the answer to part A for that second example. And I can move this back up if y'all need it here in a second. And the answer to part B is negative 637.7 kilojoules per mole. Okay. So get those answers in so you can practice, check your work. Does anybody need me to move the paper back up? Okay. I will make sure I upload this video as well so y'all can watch it again if needed.